Hey, this is Leach with Simpson Math, and in this video, I'm going to be going through probabilities with two-way tables, just some quick examples, just to kind of maybe help you out, help you refine your understanding just a little bit. So let's take a look at this first one. This says multi-generational families can be categorized as having two adult generations, such as parents living with adult children, skip generation families, such as grandparents living with grandchildren, and three or more generations living in a household. So that would be like the grandkids, the parents, and then those kids' grandparents or those parents' parents. You get the idea. A survey was conducted on multi-generational households. So everyone in this study is a multi-generational household. The reported results appear in the accompanying table, as we can see down here. We're going to use the table to complete parts A through C. All right, so first up, what's the probability that a multi-generational family is Hispanic? So when answering these probability questions, sometimes we have to be mindful of what they're asking, and specifically, what is our total? What is out of who? Well, when they're talking about this multi-generational family, that's kind of the total, what I'm calling like this total. It's the we have a total, it's those overlapping, it's the total. So it's out of all the multi-generational families. What's the probability I reach in this bag of multi-generational families and I reach in and pull out one that is Hispanic? Well, I see that there are 292 Hispanic families. Notice that this is a marginal distribution or probability. It's asking nothing about the type of family structure, just their heritage, lineage, or race. So we have here just this 292 out of the total of 1438. And so that is our probability. When I do that division to 3 decimal places, I get the about 20%, 0.203. Question B, what is the probability that a multi-generational family selected at random? So notice there, it's sounding like they're talking again about the total. Out of all of the families in this study, what's the probability that one of those families is a black two adult generation family? So this is an and or a joint probability, or there's an implied and here that they are black and a two adult generation family. We formally call that a joint probability. So this 123 is my intersection of the two adult generation and the black family, black families. And then out of our total is this 1438. So that's where I'm doing it this way. Notice it is not a conditional. It is not among the black families. What's the probability we select a two adult generation? That would be a conditional out of the let me fix my oval. It'd be conditional 123 over 250. That would be among the black, or given that they're a black family, what's the probability they're a two adult generation? Or among the two adult generations, what's the probability we select one of those families and they consider themselves black? So we have to be careful about what this is asking. This is just that and. So just a quick little multiple choice that matches it. That first one we did was a marginal probability, and that second one we did was a joint probability. So then as you see here, I skipped my math. The division is the 123 over the 1438, and we get that 0.086. All right, I forgot to highlight it. Oh well, this should be purple, and it should be then that orange. All right, so multi-generational families, again, can be categorized. It's the same question, same situation. New question, the numbers are slightly different because it's just kind of randomly generated values. But now we have the question here. What's the probability that a randomly selected multi-generational family is a two adult generational family? We, in our English ears, like to hear the conditional statement first. In probability questions, they're not always given first, but in our common speak, that is often the case. So notice here, this is the way that the wording of this problem is. It's implied that we're selecting among the black multi-generational families. Remember, all of these are multi-generational families, so really it's just among these black families in the study. What's the probability I reach into the bag of just black families and I pull out two adult generational families? So I'm talking about pulling things out of a bag because I kind of imagine that I have 1,438 ping pong balls. On 507 of them, I have the words written white, 2 adult gens. On 54 of them, I have white, 2 skip. 225, I have 3 or more, and white written. So imagine I have all of those ping pong balls written down in a big old bag, but then I go, ooh, I'm just interested in the black families here in this study. So I'm going to sort through my balls, ping pong balls, and I'm just going to make a bag of just the black families. So now I have a ping pong ball of, well, it would be of 250 total ping pong balls, and 139 of them are the ones that I'm looking for. They match my 2 adult generational families here. So that's where I get my 129 out of 250, which is about 0.516. All right. What is the probability that a randomly selected multi-generational family is white, given that it is a skip generational family? So notice it's the probability here is I'm randomly selecting. Oh, sorry, I got thrown for a second. The key with this is this word given. They're applying this given here, given that it's a skip family. So now they're putting the condition second. That kind of hurts our English ears a little bit. That pause I was a little bit confused about. So I'm selecting a multi-generational family. There's kind of the end of that kind of statement. So what's the probability that we get a white family given here? Notice here, this is a randomly selected black multi-generational family is. Okay, that is what we want to know. Here, this randomly selected multi-generational black family, that was attached to the given information here. This given is after that. They kind of throw in the given as like an afterthought. So we've got to be careful about how it's worded. So here, the given is the skip generation, so that's the 99. So I'm going back through all my ping pong balls, sorting through them. I was like, oh, this one has skip. This one has skip. This one doesn't, throw it out. So I go through, and now I have a bag of 99 ping pong balls. You can kind of, imagine the bag drawn like here. So here's our little bag. Here's a little bag of things. There's 99 in them, and I'm interested in the 54 that are white. So we have 54 over 99, and we get about 54.5% or 0.545. This one, they just straight up give it to you in the probability notation. So what's the probability that we get a 3 or more generation given the fact that they're Asian? All right, that they're an Asian family. So on here, again, the Asian is my given information. I want to know this 3 or more. The given is my denominator, that 110, and I want to know, want to find out the likelihood that I get the 3 or more. So again, my bag is made up of this rectangle right here. There's 110 total, and I want that 52. So 52 out of 110 is at 0.473. All right, this last one we're going to cover it says a website reports that 50% of their users are from outside the United States, and that 50% of the users log onto the website every day. Suppose that 20% of their users are United States users who log on every day. Now let's complete these questions. What percentage of their website's users are from the United States? That's just grabbing the given information. So if it says that 50% are from outside the United States, well, this is kind of an either or. They're either outside or they're inside. This is a yes or no. So because of that, since this is 50, 100% minus 50% is then also 50% out of a air quote coincidence, but obviously these need to add to 1. It just happens that they'll be the same number if one of them is 50%. What type of probability is the 20% mentioned above? So this 20% right here, notice I'm talking about United States users and whether or not they log on every day. So we're talking about whether they log onto the website or they don't. So those are my 2 attributes. This is a joint probability because it's an inherently and statement. I'm talking about both of those, not a condition, and that's not even one of my options anyway. All right. Oh yeah, other the options. Personal probability, it's not a personal that would be like a personal or anecdotal. They're looking at the data. They're not just, oh, I feel like 20%. No. So it's not that. Empirical is would be just our kind of a more of a small set kind of observed data, or like we just do it a few times. This is a website. This is their big set of data, and we're randomly selecting from this big probability. So what's the probability I select one of these people? So I'm getting the theoretical probability from that anyway. So it's not an empirical thing. So the real only question is it marginal or joint? Marginal would be one of these first sentences, not the intersection here. So then now we need to fill in the table. So it is just a 2x2 table with our totals. If I'm drawing the tables, I like to have a clear dividing line between my totals and my regular cells. So imagine that those are there. So if I'm filling this in, 50% are from outside the United States. So I would put that 50% here. And then 100 minus that is the other 50%. This question doesn't supply any percent symbol, so that's why I'm putting it in as 0.5. Our total will be 1, because when I add these up, I get 1, or 100%. 50% log on every day, so 50% log on every day, 50% no. So if I didn't have any of this information here, and I didn't have this 0.2, there's literally an infinite number of combinations that I could put in here that would satisfy that. So I need one more number, and that says 20%. So 20% log on every day and are in the United States, and so this is where that 0.2 comes from. And then to get the others, these other three, we just subtract. 0.5 minus 0.2 is 0.3, 0.5 minus 0.2 is 0.3, and then whatever you get to the last one, I kind of like to do it in both directions. So obviously 0.5 minus 0.3 is 0.2, and then the same is true for here. 0.5 minus 0.3 is 0.2. All right. So now that we have that filled in, let's answer this question. What's the probability that a user is from the United States given that he or she logs in every day? So it's a probability of US given logs in every day. So I'm going to look at my table here. So this is a given statement. So who am I interested in? I'm only interested in the logs in every day. So the does not log in every day, the totals, they're dead to me. My bag is basically out of this. So I do have probabilities reported in here instead of number of. So this is a different way of doing a two-way table. In our previous example, it was the counts. Here, this is the probabilities. The math is going to be just the same. You can kind of imagine it's like 20, 30, and 50. It's because the proportions are going to be the same. If I did 20 over 50, if I can write a 5, good grief, 20 over 50, I'm going to still get 0.4. Or 0.2 over 0.5, I'm still going to get 0.4. So again, these are dead to me. Here's my bag. So I'm going to imagine that there's, let's say, 50 ping pong balls. 20 of them are labeled United States, so 20 over 50, or in this case, these proportions 0.2 over 0.5, and we get this 40% or 0.4. Lastly, are from United States and log on every day independent. So I'm going to go ahead and jump down to my work that I did for this. Remember kind of my phrasing that I had for this. What do you say by yourself? Does it equal what you say given you're with somebody else? All right. So what does US say by itself? Well, I've copied my table down here so I can annotate it. Well, what does US say by itself? So US says by itself, I'm ignoring all the log on every days, and I'm just looking in this bottom row. So my total is 1, and I have 0.5 for my United States, so 0.5 over 1. Obviously, that's going to just be 0.5 in the end. So we have that for what does US say by itself? 50%. By the way, we already found that number in part A. Then, what does US say given is with something else? Given is with logs on every day. Well, remember I said draw these ovals, draw your comparisons. This 0.5 over 0.1, these need to be drawn parallel to each other. So they could be in a different situation. I could have done logs on every day by itself and compare it to logs on given United States. That would work, but I haven't already found those numbers. Notice this one we already found in part D, so that's why I'm reusing these values. So again, parallel to it, and this is given logs on every day, so all of these are dead to me. So this is the 0.2 over 0.5. And so I notice that I get 0.5, which is 50%, and this simplifies to be 0.4. That does not equal each other, and it's 10% off, and for a website, the 10% is going to be a big enough deal. So we're going to say no, these are not independent because the conditional probability that the individuals from the United States, given they log on every day, a lot of words to say this thing we found in D, does not equal to the probability of the individuals from the United States. A lot of textbooks will define independence with this equaling this after. I like the way that I presented it to y'all because it kind of matches the story of just what am I saying by myself? Does it equal what do I say given it's with somebody else? Because when I do it that way, then I know that I need to write what I'm saying by myself given first and not somebody else given me. So that's kind of weird. So anyways, that's why I have it that way. And that's the one that matches that statement because it does not equal. Here we say question mark, but really it's not equal. All right. So there's just some quick examples about the two-way table probabilities culminating in this independence. So hope seeing these further examples help. If you want to stick around for more probability videos, check me out the next one. I'll see you there. See you in the next one. Bye.